Section 4.3 Acids, Bases, and Neutralization Reactions. Many acids and bases are industrial and household substances, and some are important components of biological fluids. Hydrochloric acid, for instance, is an important industrial chemical and the main constituent in gastric juice, or your stomach. Acids and bases are also common electrolytes. Acids. As noted in section 2.8, acids are substances that iodize in aqueous solutions to form hydrogen ions. Because a hydrogen ion consists of a proton and an electron, or hydrogen atom consists of a proton and electron, a hydrogen ion is simply a proton. Thus, acids are often called proton donors. Molecular models of three common acids are shown in 4.6. Each have white hydrogens to donate. Protons in aqueous solution are solvated by water molecules, just as other cations are. In writing chemical equations involving protons in water, therefore, we write H+. Molecules of different acids ionize to form different numbers of H+ ions. Both hydrochloric acid and nitric acid are monoprotic acids, yielding one proton per molecule of acid. Sulfuric acid, H2SO4, is diprotic, one that yields two hydrogen ions per molecule of acid. The ionization of sulfuric acid and other diprotic acids occur in two steps. Sulfuric acid dissociates into a proton plus hydrosulfic or bisulfate ion, and then the bisulfate ion itself is acidic. It dissociates into hydrogen ion plus sulfate. Although sulfuric acid is a strong electrolyte, only the first ionization is complete. Thus, aqueous solutions of sulfuric acid contain a mixture of protons, bisulfate ions, and sulfate ions. The molecule acetic acid that we have mentioned frequently in the primary component of vinegar. Acetic acid has 4 hydrogens, but only one of them, the H in the COOH group, is ionized in water. The 3 other hydrogens are bound to the carbon and they do not break their carbon-hydrogen bonds in water. Figure 4.7, hydrogen ion transfer. A water molecule acts as a proton donor, acting as an acid, and ammonia acts as a proton acceptor, base. Only a fraction of the ammonia molecules react with the water. Consequently, ammonia is a weak electrolyte. Bases. Bases are substances that accept or react with proton or hydrogen ions. Bases produce hydroxide ions when they dissolve in water. Ionic compounds such as sodium hydroxide, potassium hydroxide, and calcium hydroxide are among the most common bases. When dissolved in water, they dissociate into ions, introducing hydroxide ions into the solution. Compounds that do not contain hydroxide ions can also be bases. For example, ammonia is a common base. When added to water, it accepts a hydrogen ion from the water molecule and thereby produces hydroxide. Ammonia plus water yields ammonium plus hydroxide. Ammonia is a weak electrolyte because only about 1% of the ammonia forms ammonium and hydroxide ions. Strong and weak acids and bases. Acids and bases that are strong electrolytes or completely ionized in solution are strong acids and strong bases. They are weak electrolytes or partly ionized are weak acids and weak bases. When reactivity depends only on hydrogen proton concentration, strong acids are more reactive than weak acids. The reactivity of an acid, however, can depend upon the anion as well as the hydrogen ion concentration. For example, hydrofluoric acid is a weak acid, only partly ionized in aqueous solution, but is a very reactive and vigorously attacks many substances, including glass. The reactivity is due to the combined action of the hydrogen proton and the fluoride ion. Table 4.2 lists the strong acids and bases that are most likely to encounter. You need to commit this information to memory in order to correctly identify strong electrolytes and write net ionic equations. The brevity of this list tells us that most acids are weak. For sulfuric acid, as we noted earlier, only the first proton completely ionizes. The only common strong bases are the common soluble metal hydroxides. Most other metal hydroxides are insoluble in water. The most common weak base is ammonia, which reacts with water to form hydroxide ions. Table 4.2, Common strong acids and bases. There are 6 strong acids and 6 strong bases. Hydrochloric acid, hydrobromic acid, hydroiodic acid. Those are all group 7 hydroxide or hydrogen plus group 7. Chloric acid, perchloric acid, nitric acid, and sulfuric acid. And the sulfuric acid is only strong in its first protonation. Strong bases, group 1 metal hydroxides, lithium hydroxide, sodium hydroxide, potassium hydroxide, and heavy group metal 2 hydroxides, calcium hydroxide, strontium hydroxide, barium hydroxide. This list lists 9 strong bases. Identifying strong and weak electrolytes. If we remember the common strong acids and bases, and also remember that ammonia is a weak base, we can make reasonable predictions about the electrolytic strength of a great number of water-soluble substances. Table 4.3 summarizes our observation about electrolytes. To classify a soluble substance as a strong electrolyte, weak electrolyte, or non-electrolyte, we work our way down and across this table. We first ask whether the substance is ionic or molecular. If it's ionic, it's a strong electrolyte. The second column of Table 4.3 tells us that all ionic compounds are strong electrolytes. If the substance is molecular, we ask whether it's an acid or a base. If it's an acid, it either has H first in the chemical formula or it contains the COOH group. If it's an acid, we use Table 2 to determine whether it's a strong acid or a weak electrolyte. All strong acids are strong electrolytes and all weak acids are weak electrolytes. If it's an acid is not labeled in 4.2, it's probably a weak acid and therefore a weak electrolyte. Table 4.3, Summary of the electrolytic behavior of common soluble ionic and molecular compounds. All ionic compounds are strong electrolytes, none are weak, and none are non-electrolytes. Strong acids are strong electrolyte molecular acids. There are weak acids and weak bases are weak electrolytes, and all other compounds are non-electrolytes. If our substance is a base, we use 4.2 to determine whether it's a strong base. Ammonia is the only molecular base that we consider in this chapter, and Table 4.3 tells us it's a weak electrolyte. Finally, any molecular substance that we encounter in this chapter that's not an acid or ammonium is probably a non-electrolyte. Neutralization reactions and salts. The properties of acidic solutions are quite different from those of basic solutions. Acids have a sour taste, whereas bases have a bitter taste. Acids change the colors of certain dyes the way that differ the bases affect those same dyes. This is the principle behind the indicator known as litmus paper. In addition, acidic and basic solutions differ in chemical properties in several other important ways that we explore in the chapter and in later chapters. When a solution of an acid and a solution of a base are mixed, a neutralization reaction occurs. The products of the reaction have none of the characteristic properties of either the acidic solution or the basic solution. For example, when hydrochloric acid is mixed with a solution of sodium hydroxide, the reaction is hydrochloric acid plus sodium hydroxide yields water plus a salt. Figure 4.8, litmus paper. Litmus paper is coated with dyes that change color in response to exposure to either acids or bases. Bases turn litmus paper blue, acids turn litmus paper red. Water and table salt, sodium chloride, are the products of the reaction. By analogy to this reaction, the term salt has come to mean any ionic compound whose cation comes from the base, for example, sodium from sodium hydroxide, and whose anion comes from an acid, for example, chloride from hydrochloric acid. In general, a neutralization reaction between an acid and a metal hydroxide produces water and a salt. Because hydrochloric acid, sodium hydroxide, and sodium chloride are all water-soluble strong electrolytes, the complete ionic equation associated with the equation is, when all the spectators are dropped out, it's hydrogen ion plus hydroxide ion yields water. So a neutralization reaction produces water. Equation 414 summarizes the main feature of this neutralization reaction between any strong acid and any strong base. Hydrogen ion aqueous plus hydroxide ion aqueous combines to form water. Figure 4.9 shows the neutralization reaction between hydrochloric acid and the water-insoluble base, magnesium hydroxide. The molecular equation, magnesium hydroxide solid plus hydrochloric acid, yields magnesium chloride plus water. The net ionic equation is that water plus hydrogen ion plus hydroxide yields water. Notice that the hydroxide ions, this in a solid reactant, and the hydrogen ions combine to form water. Because the ions exchange partner, neutralization reactions between acids and metal hydroxides are metathesis reactions, or double displacement reactions. Adding just a few drops of hydrochloric acid would not be sufficient to dissolve all of the magnesium hydroxide, called nickel magnesia. Why not? Figure 4.9, neutralization reaction between magnesium hydroxide and hydrochloric acid. Milk of magnesia is a suspension of water-insoluble magnesium hydroxide in water. When sufficient hydrochloric acid is added to the reaction, ensues that leads to an aqueous solution containing magnesium cations and chloride ions. Neutralization reactions with gas formation. Many bases besides hydroxide react with hydrogen ions to form molecular compounds. Two of these that you might encounter in the lab are sulfide ion and the carbonate ion. Both of these anions react with acids to form gases that have low solubilities in water. Hydrogen sulfide, the substance that gives rotten eggs their foul odor, forms when an acid such as hydrochloric acid reacts with a metal sulfide such as sodium sulfide. The molecular equation, 2 hydrochloric acid plus sodium sulfide yields hydrogen sulfide gas plus salt. The net ionic equation is that hydrogen ion plus sulfide ion yields hydrogen sulfide gas. Carbonates and bicarbonates react with acids to form carbon dioxide. Reactions of carbon dioxide and carbonate and bicarbonate with a weak acid gives carbonic acid. For example, when hydrochloric acid is added to sodium bicarbonate, baking soda, the reaction is hydrogen plus HCl yields to salt, and H2CO3, which is carbonic acid, but carbonic acid is unstable. If present in the solution of sufficient concentration, it decomposes to water and carbon dioxide gas, which escapes from the solution as a gas. The overall reaction is summarized by the equations. Hydrochloric acid plus baking soda yields salt plus water plus carbon dioxide. The net ionic equation is hydrogen ion plus bicarbonate ion yields water plus carbon dioxide. Both a baking soda and sodium bicarbonate or sodium carbonate are used as neutralizers in acid spills. Either salt is added until the fizzing caused by the carbon dioxide gas formation stops. Sometimes sodium bicarbonate is used as an antacid to soothe an upset stomach. In the case, the bicarbonate acts with the stomach acid to form carbon dioxide. Makes you burp.